Who in the world would go to Arizona to see the work of glaciers? I would. The San Francisco peaks sit a mile above Flagstaff, 12,633 feet above sea level. During the Quaternary, ice carved their highest ridges into bowls called cirques like this one. Later, after the climate warmed and glaciers disappeared, the peaks were littered with lines of loose rock called moraines, evidence of the glacier's passage. Of course, more northerly states like New Hampshire, Michigan, and Washington were covered by much larger areas of ice. But to see modern glaciers, we should head even further north. On this field trip, we'll look around Alaska and learn about different types of glaciers. We'll study how solid ice manages to move, and we'll see that ice creates glacial landscapes, both by eroding and by depositing rocks. Here's a map of Alaska. A few of the state's glaciers are found high in the Brooks Range and in the Alaska Range, but most are further south, close to the Gulf of Alaska. You see, it's not enough to be cold. Glaciers can only grow where temperatures are consistently cold and where there's plenty of snow, the raw material for glacial ice. For instance, the Alaskan interior around Fairbanks gets terribly cold in winter, but it remains glacier-free because there's just not enough precipitation. The mountains above Juneau, though, are cold enough in winter and receive 100 feet of snow every year, so many glaciers are born in this Juneau ice field. Glaciers form over many years in regions where more snow falls in winter than melts in summer. They're bodies of ice that move under the influence of gravity. It's possible that movement could happen if a glacier just slid downhill as an intact block of ice. But a glacier is more complicated than that. As snowflakes fall high on a glacier, their cumulative weight compresses previously fallen snow. Individual flakes gradually change into rounded granules that eventually recrystallize into larger interlocking crystals of ice. As the glacier grows thicker, crystals begin to slide over one another and the ice moves downhill as it deforms internally, slowly flowing like silly putty. Glacier formation requires cold temperatures, adequate precipitation, both cold temperatures and adequate precipitation. Alaska has a handful of huge ice fields like Juneau, Bagley, and Harding. These are not as massive as ice sheets in Antarctica or Greenland, but they're big, some several thousand feet thick and covering hundreds or even thousands of square miles. There are also a couple of massive Piedmont glaciers like the Bering and Malaspina near Yakutat, which rest on flat ground along the coast. They're fed by numerous small glaciers descending from the St. Elias Range. Valley glaciers are far more common in Alaska. These form in mountains and flow downhill, abrading the bedrock like a giant rasp and plucking boulders from the valley floor. They carve valley floors into a smooth U-shape called a glacial trough. By way of contrast, rivers in mountainous areas typically focus their cutting power on relatively narrow streams, thus carving V-shaped valleys. The surface of a glacier is often a tortured landscape. As ice flows around a bend or over an obstacle, it's stretched and torn into crevasses. These cracks, in the brittle upper portion of a glacier called the zone of fracturing, may extend down from the surface 100 feet or more. During summer, the part of a glacier at lower elevation begins to warm, and meltwater begins to flow. The water either makes its way to the glacier's edge or falls into ominous moulins, manholes that drain into the glacier's mysterious inner plumbing. Ultimately, this water will flow under and then out from beneath the glacier, emerging as a milk-colored stream carrying vast quantities of finely ground sediment called rock flour. Rocks frequently tumble down the walls that enclose a valley glacier. Sometimes big landslides will roll far out onto the glacier's surface. These two landslides rumbled onto Buckskin Glacier in Denali National Park. If you were looking down from the plain 10 years later, you would see that the middle of the glacier has been moving faster than its sides. More often, individual rockfalls pile up along the glacier's edge to become a sinuous ridge of loose material called a lateral moraine, which can be left behind after the ice has vanished. When two valley glaciers flow together, their shared lateral moraines are carried along as a single medial moraine. When the front of a glacier is stationary, it dumps an unsorted mix of rock debris at the terminus. This ridge of till is called an in-moraine. Some individual boulders, called erratics, are left stranded after a glacier melts. So back in New Hampshire, or even Arizona, When you stumble on an isolated boulder of an unexpected rock type, it might be worth asking, did a glacier once carry this boulder here? A glacier that manages to flow all the way to the sea before melting is called a tidewater glacier. These usually don't extend seaward as large floating ice shelves, as happens in Antarctica. Instead, upon reaching the ocean, Alaskan tidewater glaciers tend to calve icebergs close to the shore. The end moraine often protects a tidewater glacier from rough water of the open ocean that would otherwise hasten its retreat. You might be surprised that most glaciers in Alaska are considered warm, because, unlike Antarctica or Greenland, their ice is always within a few tenths of a degree of melting. At the South Pole, temperatures are so low that ice there exists well below the melting point. These cold glaciers are frozen to the bedrock on which they rest. The warm glaciers of Alaska, on the other hand, have a thin layer of water separating ice from rock. As a result, they're able to slide downhill far more rapidly than cold glaciers, sometimes hundreds of feet per year. Because of this difference in speed, the ice of an Alaskan glacier is likely to be only a few hundred years old, while ice in Antarctica might be 500,000 years old. As glaciers move downhill, they descend from high cold regions to lower warmer conditions. A glacier will advance as long as, overall, it accumulates ice faster than it melts. If the snow up above has been accumulating at exactly the rate that ice is melting down below, the glacier is in equilibrium and the terminus remains stationary. But if regional snowfall decreases or the atmosphere becomes warmer, then the equilibrium shifts and the glacier begins to retreat. This is the case for most modern glaciers in Alaska. In the lower 48, Glacier National Park in Montana may soon have no glaciers because there, and worldwide, they're retreating as Earth's atmosphere warms at an alarming rate. Glaciers are all about ice and sediment heading downhill. Marjorie Glacier carries 1.25 million cubic yards of rock to the west arm of Glacier Bay National Park every year. Think of glaciers as one of the world's most powerful conveyor belts. Sediment carried by glaciers will ultimately find a resting place, maybe the bottom of the Gulf of Alaska, where it will pile up and eventually be transformed into sedimentary rock. As such, glaciers are an integral part of Earth's rock cycle, the continuous creation, destruction, and rebirth of rock. What did you learn? The most common type of glacier in Alaska is an ice sheet, the Valley Glacier, a Piedmont Glacier. This basaltic boulder rests near shoreline in Massachusetts. There are no exposures of similar bedrock material within miles. What's the story? This is Dome Rock, 18 feet tall and sticking 12 feet below the ground. Only a glacier could have carried this erratic to its resting place at Cape Cod National Seashore.